So this is my problem sets, and kindly refer you to this problem sets as I go on and as I solve these problems in the video. So I will post this at the beginning of the video section so that it won't be very much inconvenient for you.
Hey there YouTube, now I'm going to present my assignment in engineering science, all about first order differential equation, and now I have 5 problems here. All of them are somewhat like proving and one of them is evaluation. So let's start with the first problem. The first problem states that show that the change of dependent variable from y to v defined by the substitution v is equal to ax plus by plus c will always transform the equation y prime into a separable equation. And what does this mean? So this problem states that we are going to show that given a differential, or rather given this function y prime is equals to function of this one, if we are going to substitute this with the value of v, we will obtain a separable equation whose dependent variable had changed from y to v. So I'm going to show you that. So first I'm going to write this equation dy over dx is equals to the function of ax plus by plus c. Now the problem states that if we must substitute this one with v, so we can rewrite this one as dy over dx equal to function of v, where our v is equal to ax plus by plus c. Now, how am I going to convert this into a separable equation? So first, I am going to derive v, this one here, in terms of x. So dv over dx is just equal to a times the derivative of x, which is just 1, plus b is constant, times the derivative of y with respect to x, dy over dx, plus 0 since c is your constant and the derivative of constant is equal to 0. Now, we can substitute dy over dx here with this in order to obtain dv over dx is equal to a plus b function of v. Now, rearranging this, we will obtain dv over a plus b function of v is equal to dx, and now this is a separable equation whose v variables are on the left side and x variables on the right side, and whose dependent variable is changed from from y to v. Now let's proceed to the second problem. The second problem states that show that the quotient of a homogeneous function of degree m divided by a homogeneous function of degree n is a homogeneous function of degree m minus n. So the problem simply wants us to show that if we are given a homogeneous function which has a degree n, if we are going to divide this with a homogeneous function with degree n, this will result to a homogeneous function that has a degree m minus n. So to show this one, suppose we have let's say a homogeneous function f of x y, and our other homogeneous function is g of x y. Now, if we want to determine the degree of homogeneous function, we make use of the substitution x is equal to xt and y is equals to yt, where our t here determines the degree of our function. Whatever the degree of t here is also the degree of our homogeneous function. Now, using the substitution for f of xy and g of xy, we will obtain something function of f of xt and yt. This is just equal to t raised to some degree, say for example m, times the function of x y. Now, where did I get this one? So suppose I have a function xy, say x squared plus y squared, and if I will make use of this substitution, so my function will become xt yt, where my x is just substituted by xt and my y substituted by yt, and now this will be equal to xt squared plus yt squared. Now factor in t squared so that we will determine the degree of our homogeneous function. We will have t squared times x squared plus y squared. So this squared here tells us that our homogeneous function is raised to a degree 2. Now you obtain something like t raised to some to 2. This is multiplied by function of your x, y. Now similarly, doing the same thing for your g of xy, we'll also obtain g xt and y t. This is equal to t raised to some degree, say for example n, times the function of your g, x, and y. Now the problem wants us to divide these two homogeneous functions. So dividing this one over this one, then using by law of exponents, this one will just be expressed as t raised to m minus n, and we can write the function of xy divided by the g of xy as, for example, h, function of h xy, where our h xy is a homogeneous equation, or a homogeneous function rather. So the third problem is about evaluation. So here we must find the general solution for this one. So we are going to find the general solution of x dy over dx plus 2 times 1 minus x squared times y equal to 1. Now, as you can see, this looks very similar to the general equation of your linear function, which is expressed as, so general equation for your linear differential equation, which has the form dy over dx plus function of p, function of x, y is equals to q of x. Now, we can transform this equation into its general form by just dividing this, or rather by multiplying this with 1 over x. So we can cancel x here, and this will just look like this. So multiplying this by 1 over x, we have dy over dx plus 2 over x minus 2x times y is just equal to 1 over x. So in order to solve your linear differential equation, after converting it into its standard general form, we are going to multiply the standard general form with the integrating factor. Now, what is an integrating factor? So let's go back to the general equation of linear differential equation. Now, from here, based on this equation, our integrating factor, let's denote that as v, is equal to the e raised to p of x, integral of p of x. You are going to integrate this with respect to x. So for our case here, our p of x here is this one. So finding the integrating factor, we have v equal to e raised to, I'm going to factor out 2 times the integral of 1 over x minus x. This will be integrated with respect to x. So integrating this one, I will obtain e raised to the natural log of x squared minus x squared. Now, how did I get this? The natural log for your 1 over the integration of your 1 over x is equal to the natural log of x. Now, this one, if I'm going to integrate this will be 2 natural log of x minus 2 times x squared over 2. So this will just cancel, and by law of exponent, this will just become natural log of x raised to 2. And then by using the laws of exponents, I can express this as e natural log of x squared over e raised to x squared. And by using the property that e raised to natural log of x is just equal to x, I can rewrite this one as x squared times e raised to the negative x squared. And this is our integrating factor. So after obtaining your integrating factor, you are going to multiply this integrating factor with your general form of equation. So multiplying this with your integrating factor, x squared e to the negative x squared. So I will obtain, for the right hand side, I'm going to use a shortcut. So the left hand side rather is just equal to the derivative of your dependent variable, which is for this case y, times your integrating factor x squared e raised to the negative x squared. You may want to verify this, but I'm just going to proceed with this one. And for your right hand side, this is just equal to just multiply this one, so you will have x times e raised to negative x squared. Now we will be integrating both sides in order to solve for y with respect to dx. Now before integrating the right hand side, we must use the substitution. Like we have to use let u be equal to negative x squared, and now du is just equal to negative 2x dx. Now since I have x dx here, I may want to express this as du over the negative 2 is equal to x dx. Now using the substitution, evaluating this will just yield to y x squared e to negative x squared. Now why is that? Because you are just referring to the you are getting the derivative of this at the same time getting the antiderivative, so you will just result to this one. So this expression is just equal by using your substitution. X dx is equals to negative 1/2 du. So I will put negative 1/2 on the outer side. So I have negative 1/2 integral of your negative x squared is equals to u e raised to u x dx, which is just du. Now we can integrate this one. So y x squared e to the negative x squared is just equal to negative 1/2 e by substituting u back to its original form, since the integral of e to the u is just equal to e to the u, so this is negative x squared, and don't forget the plus c, which is the constant. Many of us just got everything mixed up and wrong because we forgot plus c. Now solving this equation in terms of y, I will have y times x squared is equal to, first I will multiply this by e raised to x squared. I will obtain c e raised to x squared minus 1/2. Now y here is just equal to 1 over x squared times c e raised to x squared minus 1/2, and this is our general solution for the given problem. Now I am down to problem number 4. Here this involves Clairaut's equation. It says that given a Clairaut's equation of this form, we have to show that its general solution is of this form, and also that the parametric equation, this and this, is just a solution from your Clairaut's equation. Now you can refer from the problem at the beginning of this video. I'm going to show it to you, that I had showed to you. Now the Clairaut's equation, we are given with Clairaut's equation, which is equal to y equal to x y prime plus function of y prime. Now I will let t equal to y prime, which is, this is just equal to dy over dx. Now Clairaut's equation, usually they don't use really the variable t but rather the variable p, but for my case I will use t, so that from our problem, this one I will obtain this as a parametric solution, and this is in terms of p, so I am going to use t. Now making the substitution, I will have y equal to xt plus my function, which is now expressed to t. So getting the derivative of this with respect to x. Now why am I getting the derivative with respect to x? Because this is derived in terms of x, so I may cancel this t and here. I will show you later. So now getting the derivative with respect to x, I have dy over dx is equal to, we are going to use chain rule here, so first times the derivative of the second, so first, which is x, derivative of the second, dt over dx, plus the second, which is t, times the derivative of first, which is just equal to 1, plus the derivative of your function of t, the derivative of this is just equal to df over dt times dt over dx, and so that I will get df over dx afterwards. Now, solving this equation, take note that our t here is just equal to dy over dx, so I may cancel t here as well as dy over dx, and I will obtain 0 is equal to factoring dt over dx, so I will have dt over dx times x plus df over dt. Now, my first root here is dt over dx is just equal to 0, and since I am looking for a value of t here, I am going to integrate this one with respect to x. So integrating both sides, I will have t is equal to the integral of 0 is, let's say this is just equal to a constant, and let's label a constant m. And for our second root, which is this one, so our x here is just equal to the negative of df over dt, and this can just be expressed as negative derivative of the function with respect to t. Now, substituting this value to here, we will get equation, rather we will get the general solution of the Claudius equation. So y here is just equal to mx plus function of your m, where m is just any constant and thus makes this a general solution. Here, this one we can replace the value of x here, and we will obtain a specific solution. I think that was called a singular solution for Claudius equation, which is just equal to y equal to negative t function derivative of t plus f of t, and this is our particular solution, which verifies the given parametric equations in the problem. This one, which is a solution from our Claudius equation, and we obtain this one, which is a particular solution of our Claudius equation. And finally, for number 5, this is an application of Newton's law of cooling. Now, just refer to the problem at the beginning of this video. So I am going to speed things up. I'm going to write the given here. So we are given, I will make first a table, time and the temperature of your ball and the temperature of your water. So time here is equal to 0. For this box, this is equal to 15 minutes. And by the way, I would like to refer back to the problem in this statement here. Assuming that the temperature of the ball at any instant is the same at all points, so as with water. So this assumption here is important. Maybe you were just wondering, what the hell is that? This assumption here is important because if we do not assume that the temperature of the ball at any instant is the same at all points, rather the temperature of the ball is different at all points, we have to find the temperature of the water at different points and then find the integral or sum it all up, and which is a very tedious job. So this assumption here makes everything simpler rather, not simple. So here we are given at t is equals to 0, the temperature of our ball is equal to 100 degrees Celsius, and at t is equals to 0, the temperature of our water is equal to 40 degrees Celsius. Now after t is equals to 15, the temperature of our water is now equal to 50 degrees Celsius, while the temperature of our ball is equal to 80 degrees Celsius. And we are asked from the problem to find the temperature of the ball as a function of t. We are going to find this one, and also what is the time, or what is the time when the temperature of the ball is equal to 75 degrees Celsius. So, as I said earlier, this is an application of Newton's law of cooling. Newton's law of cooling states that cooling states that the rate that the temperature change with respect to time is just equal to, or rather this is proportional. So write the proportional of constant of proportionality is proportional to the temperature of your object minus the temperature of your surrounding, labeled as Tm. So we are going to express the temperature for our ball and the temperature of our water in terms of this, and we are going to solve this equation. Now let's start with our ball. So for the temperature of our ball, we have d TB, which is the change of temperature of ball with respect to time, is just equal to the constant of proportionality equal to the temperature of our ball minus the temperature of our surrounding. Now, this is a separable equation, and we are just going to rearrange this one, and we will get something like D change of the temperature of the ball is over temperature of the ball minus temperature of your surroundings equal to K dt. Now, how are we going to solve this equation? Take note that the temperature of your surrounding is constant. This does not change over time. So we can treat this one as a constant. Then, let's express let u, we use again the substitution, let u equal to Tb minus Tm. And we get the derivative of du. The derivative of u is just equal to the derivative of Tb. Now, since Tm is constant, the derivative of this is just equal to 0. So, the derivative of u is just equal to the derivative of the temperature of the ball. Now, this one, we can now express this as du over u is equals to k dt. Now, getting the integral of both sides and substituting u back to this function, we will get the natural log of Tb minus Tm is equals to kt, and don't forget the plus constant. Now, where did I get the natural log? The integral of 1 over u du is just equal to the natural log of u. U here is equals to Tb minus Tm. Now, in order to solve this one in terms of Tb, we will use again the property that e raised to the natural log of x is just equal to x. So, raising both sides by e, so exponent, I will have Tb minus Tm, since my x here is just equal to Tb minus Tm, and this is equal to e raised to kt plus c. Now, using the properties of the exponent, I can rewrite this as e raised to kt times e raised to c. But this one is just a constant, another constant. Let's label that constant at c2. So, this is just equal to c2 times e raised to kt. Now, I can finally derive the function of temperature of ball with respect to time, and this is just equal to C2 e raised to kt plus Tm. And this is not yet the function of the temperature of the ball with respect to time, since we still need to solve for the temperature of your surrounding, the constant C2 as well as the K. Now, if you are going to use the similar process for here, we will obtain that the expression or the temperature of water with respect to time is just also equal to, similarly to this, except that the constant here is different. So, let's label that one as C4 e raised to kt plus Tm. Or you can use any other variable aside from C4 as long as that is constant. So, to show you that this one, how to get this one, let's again solve for now Tw. For Tw is still the same, dTw over dt. This is the Newton's law of cooling expression, Tw minus Tm. Now we have dTw over Tw minus Tm equal to k dt. Getting the integral of both sides, I will have natural log of Tw minus Tm is just equal to kt plus c. Now, raising this one to the e, this I will get Tw minus Tm. This is equal to this one. Still use another constant, which we say C4 e raised to kt. Now, temperature of water with respect to time is just equal to C4 e raised to kt plus Tm. So, it's just equal to that one. Now, the next thing we're going to do is we have to solve for the temperature of the surrounding. So, to solve for the temperature of your surrounding, we are going to use this data given here. Now, we are given that at temperature which is equal to 0, the temperature of your ball is equal to 100 degrees Celsius, while of that of your water is 40 degrees Celsius. So substituting this data here, we will get for the temperature of your ball, we will have 100. I'm referring to this equation, first one, is just equal to C2E. Take note that t here, the time here is equals to 0, so this is just e raised to 0, but e raised to 0 is just equal to 1. So this is just equal to C2 plus Tm. Now we are going to solve for C2, so C2 here is just equal to 100 minus Tm. Now why am I solving for C2? I am solving for C2 so that I can express the right-hand side of this equation in terms of Tm, so that I can solve for the temperature of the surrounding, using also, but equating it here, the temperature of the water. Now, in terms of the temperature of the water at 0 degrees Celsius is equal to 40. Based on the data here, 40 is just equal to C4. E is just e to raise to the 0 is just equal to 1, so this will be plus Tm. Now, solving for C4 is equals to 40 minus Tm. So, substituting this value back here, I will obtain Tb, function of temperature of ball with respect to time, is equal to C2 is equals to 100 minus Tm times e raised to kt plus Tm, while my temperature of water with respect to time is now equal to 40 minus Tm e raised to kt plus Tm. Now, solving both sides for e raised to kt so that we can equate them, the two. So we will have, for temperature of your ball, we will have e raised to kt is just equal to temperature of your ball with respect to time minus Tm over 100 minus Tm. And for your water, we have e raised to kt is just equal to temperature of your water with respect to time minus Tm over 40 minus Tm. Now, since both of this are equal, so say for example we are going to use the data at temperature which is equal to 15. So for your water, for your ball here, we can express that after 15 minutes, so we have e raised to 15k is just equal to temperature of your ball is 80 minus Tm over 100 minus Tm, whereas for your water, we have e, still a raised to kt is just equal to temperature of your water here is 50 minus Tm over 40 minus Tm. Now, since both of them are this e raised to, this is 15k. Since both of them are equal, we can equate this one also. So we have 80 minus Tm over 100 minus Tm. This is just equal to 50 minus Tm over 40 minus Tm. Now, cross multiplying this, I will have 3,200 minus 80 Tm minus 40 Tm plus Tm squared. And also, this is just equal to 5,000, cross multiply, minus 100 Tm minus 50 Tm plus Tm squared. Now, simplifying both sides, I will have 3,200 minus 120 Tm is just equal to 5,000 minus 150 Tm. Cancel Tm squared there. So, combining like terms and solving for Tm, I will have 30 Tm is just equal to 1,800. So Tm here is just equal to 60. So the temperature of our surrounding is just equal to 60 degrees Celsius. Now, substituting this one back to our equation, our general form, not really the general, but this equation, substituting back the value of Tm, we will only look at Tb here since the problem only asks us to derive this one. So our function now of Tb is just equal to Tb of T Therefore here is just equal to C2 e raised to kt plus the temperature of our surrounding, which is just equal to 60. Now, this is not the function of temperature of the ball with respect to time yet, since first we have to solve for your C2 and we also have to solve for the value of K. Now, in order to solve for the constant C2, we must refer again to the table. So we must pick this value so that here this one would just be equal to 1 and we can solve for the value of C2. So the temperature of the ball again at time 0 minutes is just equal to 100 is equal to C2, and e raised to 0 is just equal to 1 since t is equals to 0 plus 60. So our C2 here is just equal to 40. So we can now write this as TB function of t is just equal to 40 e raised to kt plus 60. Now finally we need to solve for the value of k. To solve for the value of k, we use this data. So we have it here as, so the temperature at T is equals to 15, the temperature is equal to 80 degrees Celsius. So the TB here is just 80 is equal to 40 e raised to 15 K. I'm referring to this equation plus 60. Now solving for your K here, I will have 80 minus 60 over 40 equals to e raised to 15k. So this one, 80 minus 60 is 20 divided by 40 is equals to 0.5. So I will have 0.5 equal to e raised to 15k. So getting the natural log of both sides, I will have the natural log of 0.5 is just equal to 15k. Now, where did I get this 15k? If I express this in terms of natural log, I have natural log of e raised to 15k. I can rewrite this here. So I have 15k by law of the logarithms is equals to natural log of e. But the natural log of e is equals to 1, so this expression is just equal to 15k. Now solving for k, the value of our k here is just equal to the negative 0.0462. And finally, substituting this value of k from our equation here, as long as the value of our temperature of surroundings and temperature of our constant, we will obtain the temperature of water as a function of time as TB, a function of t is equals to value of our constant. The value of our constant here, C2, is just equal to 40 e raised to, value of our k is negative 0.0462 t plus temperature of our surrounding, which is just equal to 60. So this is our the temperature of the ball as a function of time. Now the next question is we have to find the time that is needed for the temperature of the ball to reach 75 degrees Celsius. Now just substituting this TB function of time equal to 75, I'll have 75 is just equal to 40 e raised to negative 0.0462 t plus 60. So we have 75 minus 60 over 40 is equal to e raised to negative 0.0462 t. So this is equal to 3 over 8 equal to e negative 0.0462 t. Getting the natural log of both sides, I will have the natural log of your 38 is just equal to negative 0.0462 t. Now solving for t is just equal to 21.2 minutes, and this is the answers. So that ends my problem sets. I hope you learned something, or I hope you understood it, and bye bye.